I'm Silly Dang, a 6-year PhD student at Mechanical and Aerospace Engineering here at Princeton. I'm working on combustion, very cool stuff, burning stuff. So I'm trying to understand the fundamental combustion processes, fluid mechanics, chemistry coupling to really make combustion, this old science, more attractive to the broad audience. So try to make it cleaner, safer, and more higher efficiency, stuff like that. Yeah.
Can you give us an example what kind of applications people would be familiar with?
Sure, for combustions we use it in internal combustion engines. So in our case, here is a diesel engine and here is a combustor in airplane. So we are trying to understand how we generate this flame and how this flame can be stabilized where it's supposed to be so that you don't have an engine failure.
Share with us a little bit about how you got interested in combustion and how has Princeton helped you with your projects.
Sure, I'm always very interested in energy stuff. I came from China and we burn a lot of coal. So during the winter, the sky is gray. So I always interested in combustion so that we can have higher efficiency and lower emission.
So my name is TEITELBAUM. I'm with the Department of Civil and Environmental Engineering, advised by Forrest Meggers over in School of Architecture. And so here is our experimental radiant cooling pavilion. The idea is to demonstrate that you can effectively cool an outdoor space without having to change the air temperature. Because one thing that people aren't usually aware of is that air temperature is only 50% of your comfort. The other 50% is the radiant temperature, so you're always radiating and exchanging heat with walls and other surfaces around you. So if you can lower that surface temperature, you perceive a colder temperature. So we have a cooling tower back here. Water evaporates, cools the bulk water temperature down. We pump that around, and then there are these reflective areas, and that reflects that water temperature to someone standing in the middle or anywhere in the dome, but the middle is the most concentrated. And then they experience that temperature. So without conditioning the air at all, you actually lower the perceived temperature. To do that, though, because we're working outdoors, we had to develop some new sensors because other ones are really sensitive to wind. And so if it's windy, that's another factor that we're trying to eliminate from our measurements. So we developed some sensors to measure that data.
So I'm Justin Mail, and I'm with the Department of Chemical Engineering.
Hi, I'm Rebecca, and I am in the Department of Geosciences. I'm a senior.
So what we did this summer is we were testing the effect of calcite, the main component of limestone, on the formation of iron oxide crystals. So what we did was we made 4 samples, each containing aqueous iron at a certain concentration. And then we tested the effects of different calcite components on the formation of iron oxide crystals.
The applications are kind of twofold. So the first, of course, is environmental systems, right? And that's what everyone cares about. So if you look at systems in the natural world that have a lot of calcite in them, most systems also have a lot of iron. So if you look at something like a soil sample that has a lot of calcite, those are called calcareous soils. They tend to be in very arid, dry regions. And it's unclear as to what the chemical interactions between calcite and iron are. So hopefully by doing this in the lab, we can sort of elucidate what could be going on chemically between those components and possibly verify out in the field that maybe calcite is having this influence on what kind of iron oxide is precipitating out in these systems, which would have some implications for how we understand some geochemical cycles and processes. The other application is that we want to use an iron oxide coated calcite material or limestone to remove arsenic from drinking water. And we know that from the literature that iron oxides are very good at removing arsenic from drinking water. So when you use a calcite substrate, you can basically have these really tiny iron oxide crystals giving you a lot of surface area for that arsenic removal and maintain a large enough grain size for it to still be effective as a filter.
Hi, my name is MARTINA, LESSIO, and I work in the chemistry department and in the group of Professor Emily Carter. I work on CO2 reduction to liquid fuels, and to explain in more details, my work focuses on finding materials or molecules that are able to take CO2 and convert it in something useful, like liquid fuels, using a material called gallium phosphide, which is a semiconductor. So this material is able to absorb solar light, and then this solar light can be used to convert CO2 into methanol. So this process ideally will also use solar energy, so it will not require any kind of energy input. So all the energy that this material collects is employed like exclusively to produce methanol, and there are no like byproducts.
Okay, so my name is Soin Shim. I'm a grad student at mechanical engineering. So my work is actually about hydrophilic material and using water evaporation, where we made a evaporative cooler. And here, what we done is to combine like staggered structure and thin water film flow together. So having continuous water flow, we could like evaporate water like consistently in the dry environment. And in our like staggered design, like making like very open space like this, we enhance the evaporation and vapor transfer from the device, so that we have like temperature difference. Like with water flow on top of it, we have 5 degrees of temperature difference in and out of the device. So it's a promising application for like real buildings. And like in here, Forest Maker's lab, they're building like 8-foot device using the same idea with thin film of water to apply to real building.
Hello, my name is Sayed Hossein Hezave, and I'm a 5th-year PhD student at Civil and Environmental Department. Here I'm presenting my PhD research on vertical axis wind turbines. We have 2 kinds of major wind turbines: horizontal axis wind turbines, which you can see everywhere around the world, and vertical axis wind turbines, which were introduced prior to horizontal axis wind turbines, but because they didn't have much more research on them compared to horizontal axis wind turbines. They have several advantages compared to horizontal axis wind turbines. First of all, since they're rotating around the vertical axis, they can work from wind from any direction, so they're omnidirectional. And also, since their axis of rotation is vertical, their gearbox and the power generator would be located at the ground level. So the maintenance and the construction costs are going to be less expensive compared to horizontal ones. So what I'm doing is put all my effort on investigating on vertical axis wind turbines and try to see how they interact in atmospheric boundary layer. I want to focus on their characteristics, such like how is their wake deficits, and what is the shape of their wake deficits, what's their pattern, and how we can arrange these kind of vertical axis wind turbines in wind farm. When you put vertical axis wind turbines really close to each other, instead of reducing the power, they actually enhance the power productions. So we are adapting that concept in our model and creating a triangle clusters of vertical axis wind turbines.
I'm Amir Haji Akbari. I'm a postdoc in the Department of Chemical and Biological Engineering, and I work with Pablo De Benedetti. So my work is on ice nucleation, and this is a very important process that happens in the atmosphere and is basically responsible for all the rain and snow that we see in our day-to-day life. So the question that I'm particularly interested in is to use computer simulations to determine how fast ice freezes in the clouds. For the temperature that I was interested in, and I looked at, was 230 Kelvin, which is 43 degrees Celsius below the experimental freezing temperature of ice. And I observed that what I get from my calculations is that you need to wait around 1 second if you had 1 cubic meter of pure water without any impurities or any nucleating surfaces for freezing to start and complete.
So why is this important to know? What kind of practical applications does this have?
Because that's what determines the timing and the rate of precipitation in clouds, and also how much light they absorb, and the fraction of ice in a cloud is a very important parameter in climate models for predicting weather.
So I'm Hans Weerman, postdoc at the Energy Systems Group. and we look at how do you make biofuels from biomass. So we model different bioconversion techniques, in this case pyrolysis and gasification. And we determine how efficient are these processes, what's the production cost of the biofuel at the end, and what's the reduction in greenhouse gases that you can get with these systems. And because we think biomass is a limited resource, we want to make the biofuels as greenhouse gas negative as possible, because then when you add crude oil fuels, you still have a greenhouse gas neutral fuel. So we add carbon capture and storage to these processes and we see what's the effect.
My name is Dr. Jovan Pantelic. I'm a postdoc at Department of Architecture, although I'm a mechanical engineer. And the project here that we are seeing in this poster is basically redefining the way we air condition the air for buildings. So in this way, the vision is to change the way we cool the air, and basically exchange these big chillers, machines that consumes a lot of refrigerant and cause a lot of CO2 emissions, with liquid desiccant systems and evaporative cooling. So in that way, we are doing air conditioning in a more environmentally friendly way.
Is this more commercial or residential, or who can use it?
Anyone can basically use it. Of course, this project itself is in a very infant stage, so we are just looking at how this basically a proof of concept. But in maybe 3 to 5 years, this will reach a point where there will be devices that might be applied in any kind of buildings we are talking about.